So there's a few figures in this PowerPoint that I want to elaborate on. And so we have some standard conditions, some definitions. We have Dalton's law. Now this thing needs to be like the back of your hand. Partial pressures are additive. Okay. Even if the situation is non-ideal, this is the assumption we have to make. So we use Dalton's law very, we rely on it. So that, we've got partial pressures all adding up to 1 atmosphere. And we use that regularly. Raoult's law is not, we use it in certain situations and not in others. And so we'll talk about that in a second. But this is one curve that I really want to emphasize. Looks familiar, doesn't it? Okay. We were talking about the Leonard-Jones 612 potential. Okay. This is something that should be in your mind in terms of interaction of substances. Now, we were talking about it within a molecule, like a carbon, hydrogen, or even two molecules interacting with each other, and that's what we're talking about here. This is two separate molecules coming in, colliding. The ideal gas is this equation of state. So essentially, there's 0 attractions, 0 repulsions until they hit. And when they hit, there's infinite repulsion. So they hit, and there's infinite repulsion. So they bang into each other. It's called an elastic collision. All the energy that comes in is conserved. There's no energy lost to vibrations or rotations and so on. So the molecules are hard spheres. And in fact, they have no volume. Notice this one has an association. You start to interact with it at this volume, at this distance, but this one is at 0. So this right here should be 0 contact. And so as soon as they contact each other, they're point masses. They really, the ideal gas law is governed on point masses. So it's a mass and a single point. The only time they would collide is if they tried to occupy exactly the same spot in space. But real gases have some attractions, which would be this part right here. Attractions are dominant, and then repulsions are dominant up here. We can go through all the different pieces of the ideal gas law. Let's just compare real and ideal. So ideal here on the left is pressure volume, but the real situation is over here on the right, pressure volume. So these are PV phase diagrams. Always look at the axes whenever you get a graph, especially in this particular set of notes. Okay? Whenever you see any kind of diagram, go to the axes first. This is pressure and volume. Now what we have here is condensation. I even like it that it's blue. Okay, it's like water, right? It's cooling down, and then it's this beautiful blue water. So over here we have, these are isotherms. And so here, 50 degrees C, this is CO2, so 50 degrees C is that isotherm, no condensation at 50 degrees C. 40 degrees C, we start to see some funny behavior right here, but still it's a gas all the way through. At 31.04 degrees C, we have this thing called the critical temperature, critical point. And it behaves like a condensate, but there's no meniscus. It's just anything below that, you will have a meniscus. You'll actually have liquid. So let's look at this one here, this EDC. So we'll start at this point A and walk along. So what we're doing, this is the volume axis. When we move from A to B, what have we done to the sample? We've compressed it. So this is compression from A to B. It's still a gas. What happens at C? We start to have condensation. Okay. This is liquid CO2. We're at a high pressure. So we're at like 60 atmospheres. And so that would be the vapor pressure above that liquid. So you have a liquid drop inside the container, and the vapor above that container is at 60 atmospheres. And you would see a liquid drop of CO2. You would see, if it filled the bottom of the container, you'd see a meniscus. And the vapor pressure above that meniscus is 60 atmospheres for CO2 at room temperature. When you're at D, you've got half the number of moles is a liquid, half the number of moles is vapor. When you're at E, all the moles in the container are now liquid. Now, how can that be? The container has to be flexible. Think of this as a piston. So we're pushing a piston on this sample of CO2. Actually, let me just draw it on the screen. So for C, we've got a container, got a piston, it's going down because we're compressing it, and we've got a little CO2 drop in there. Okay. It's starting to condense. At D, at the container, piston's much lower, and we've got half the moles are liquid, half the moles are gas. This is probably not to scale. But the liquid's more dense, and so it takes up less volume, but half the moles are gas, half the moles are liquid. And then we've compressed this container all the way down at E. Where all the moles are liquid.
Now, there's not going to be any vapor?
No.
None?
None. Because this is a phase diagram, and now we're at the liquid phase. So the vapor phase is gone. And that's why the slope of that line goes crazy steep. Okay? Because now we're compressing the liquid. So this is actually, the slope of this line is a thermodynamic quantity. That's the isothermal compressibility of the liquid. It's very steep. Yeah. This slope of this line over here would be the isothermal compressibility of the gas. And so you change the pressure and the volume changes. Over here you change the pressure and the volume changes, but it takes a huge amount of pressure change to change the volume. And over in the gas, it takes a little bit of pressure change to change the volume. You know, so rise over run. You know, this is the pressure change that it takes here to change the volume by that much. Okay, and over here, this is the pressure change it takes to change the volume that much. Right? Because the liquids are incompressible. You know, you can compress them, but we say compared to a gas, they're not compressible. Yeah, that's important too. For the line on the left is hydraulics. The line on the right is pneumatics. So you can push things with air, you know, and actuate valves, but it's lossy. You're pushing more air than you need to get it to actuate. But hydraulics is more efficient. You push on the liquid and it pushes just as hard wherever it is at the end of the tube. And so that's why for our backhoes and everything we use liquid to push those pistons and not gas. But if we just need to flip a valve or something, we can use pneumatics because it's easier. If a gas leaks, you don't have to mop anything up. Right? But if a hydraulic system leaks, you got a mess on your hands, you know. So, and so this is a little more accurate diagram. You can see now. Notice the vapor pressure changes with temperature. We know this, right? We change the temperature and the vapor pressure increases. When that vapor pressure reaches 1 atmosphere, then that's the normal boiling point for the liquid. So these are isotherms. Now this dotted one is an ideal gas, and you can see at really high temperatures or at large volumes and low pressures. So think about a large volume and low pressure. In this room, we have a large volume and a low pressure. We're nowhere near the molar volume of nitrogen or the molar volume of oxygen. Those would be really small quantities. We could compress those to their molar volumes and get it close to the liquid area, but it would be such a small volume for this amount of oxygen, and we're much larger than that for oxygen at this temperature. So oxygen's behaving like an ideal gas in this room. We got a large volume and a low pressure. And so here's the volume of the gas there, and there's the volume of the liquid. So you can figure out the density as well. So if you knew that, if this was 1 mole of gas, then you find the volume for 1 mole, and 1 mole of liquid, you have the volume for 1 mole of liquid. You can get the densities of those. Okay, above here, now this is kind of an interesting thing. The supercritical fluid region is a smaller volume, a higher pressure, and a higher temperature than this critical point here. So from this point, let me just draw it with the pen. Draw a line straight up and a line straight over, and that's the supercritical fluid area. It's right here. Because you got to be you've got to compress it more than the critical volume, higher than the critical pressure, and higher than the critical temperature. And that's supercritical in all three. A smaller volume, but larger temperature, larger pressure. And the interesting thing about that supercritical fluid, it has the density of a liquid, but it flows like a gas. What does that mean, like flows like a gas? Well, like this container here has a meniscus, so the liquid is only down there. But if supercritical fluid, it would be this dense, but through the whole container, and I wouldn't have a meniscus.
So just to make sure I'm not misinterpreting, you drew a line straight up and you have shaded area in the ideal gas area and in the liquid area. So is it, you're saying the supercritical fluid is?
Well, I would say, ideal gas is this way. Okay, they're out of town.
Right, but I'm saying where you have the little slashes,
Yes,
where you're saying it's supercritical fluid,
yes.
it's going from the dark blue into the, where you can see the background of the grid. So say the yellow line that's coming up, it passes through your vertical line.
Yes, right here.
So is it a gas or a supercritical fluid?
At this point, it's a supercritical fluid in this region.
No matter the temperature. So if that's the case, then why doesn't the blue just go
Well,
straight
see,
up?
I probably shouldn't have drawn these lines right here. It probably should just be this region here. Because this right here is below the supercritical temperature. So these right here are actually liquids.
Okay.
You got to be above the supercritical temperature, which would be above this blue line, right? So this is the region for the supercritical fluid. So it's above that temperature, above this pressure, and smaller than this volume. So I was just sloppy in how I marked my marks. Yeah.
I get
What's bothering you?
the fact that the yellow line coming from the gas,
Yes.
the moment it crosses, even though it's at a higher temperature, after it crosses at 100, so it kind of crosses that red line that's going vertical
It
at 100
crosses.
pressure, at
Yeah, right
100
here,
100
right?
bar.
Yeah.
The moment it crosses that, it's a supercritical fluid.
Well, my line is at that critical volume. I'm drawing that critical volume. But when you're above this point right here, there's no transition. It's not like it's going along as a gas and then something immediately happens and it's a supercritical fluid. It just gets more and more dense. You can just compress that gas to where now it has the density of a liquid, but there's no event that happens. There's no phase transition. Does that make sense? Yeah, it's just now you've just had a high enough temperature and you put it in a small enough volume and it's a high enough pressure, now it's a supercritical fluid. Yeah. So it's a fluid. We call it a fluid because it's very dense, but it's like a highly compressed gas is another way to say it. Yeah. Now, this is the place right here that there is some crazy phenomenon. Like at this critical point that you're toying with condensation, and there's a lot of crazy stuff that happens. Like density fluctuates infinitely throughout the substance. You have some areas that have the low density like a gas and others have really high density like a solid. It's jumping all over the place. But that's just on that isotherm. That is the TC isotherm. And when you get to that low volume, you actually see some sort of phase transition behavior there. But above it, you lose that. And below it, you have constant condensation. Yeah. So those are great comments, great questions. I guess the most regular thing about this would be the vapor pressure. We deal with vapor pressure the most. So that's just the pressure of the vapor above the liquid. So that partial pressure of whatever the liquid substance is in the vapor phase. Okay. And that's when we distill something, we heat it up so that the vapor comes over and we condense it. Okay. And when we have a mixture, the vapors have a different composition than the liquid mixture. And that's what we're going to study next is mixtures and look at. We'll go through all the pure phase diagrams and then we'll get into the mixture phase diagrams. So these critical constants, we've seen this for CO2. Here are the critical constants for several gases. So you just kind of look at them just for curiosity's sake. So water, this is in atmospheres. So 218 atmospheres, a volume per mole of 55 mils per mole, and then a temperature of roughly 650 Kelvin. So what does that tell you? Well, at room temperature, water's a regular liquid. Okay, it's not anywhere near being supercritical. To get water to be supercritical, you have to have pretty extreme conditions, right? 218 atmospheres, that is pretty high. In terms of pounds per square inch, multiply that by 15. And so that's a lot of PSI, okay? Temperature is pretty hot, 650, whereas CO2 only has to have 73 atmospheres. That's not bad. 300 Kelvin, that's almost room temperature. 298 is room temperature. And then 94 mils per mole, you're just compressing it into a small space. So if you have a mole of gas and compress it down into 94 mils, raise it to 304 degrees, and it's going to give you, if you have 1 mole in 94 mils and it's at 304, your pressure will be 73 atmospheres, and it will be the supercritical, or it'll be the critical point for CO2. If you were to shrink the volume, raise the temperature, you would have a supercritical CO2. So that's pretty achievable. CO2 is inert. I mean, it's pretty inert. And it's got a floppy electron cloud. It's a pretty good solvent. And so that's why they use supercritical CO2 to do so many different things. The nice thing about it too is because if you get supercritical CO2, I can have a reaction vessel. I can pressurize it by pumping CO2 in there, and it can do its chemistry, okay? And then I can flow that out of the top of the vessel. It doesn't have a meniscus. Okay, so I can just keep pumping in clean CO2 and taking out whatever it's dissolved out of the top of the reaction vessel, or the side, or whatever. I don't have to worry about a meniscus. And then over here, if I have CO2 in a container, all I have to do to separate the solvent from what it's dissolved is pop the pressure. So if I drop that down to 1 atmosphere, then we have a CO2 gas now, and everything that was dissolved in that CO2 falls out. And this is how they do dry cleaning and decaffeination. So those are the 2 largest uses of supercritical CO2. It's a lot of our cleaning, like in Huntsville even, they'll have a van that drives down to Houston, and they'll have a supercritical CO2 chamber where they put your clothes in there, and they'll dissolve the grease out of your clothes using supercritical CO2, and then they will, pull that over, pop the valve, and all the grease falls out into their waste, and their clothes are clean, and they send them back up to wherever they went. And so, my clothes, I have a cleaner here in town, but they're basically a drop-off spot. They have barcodes on all my clothes, and they throw them all in a bag, and off they go to some other facility that handles either the solvents or the CO2 situation. Now, coffee beans is another thing. You have coffee beans, you pump in the CO2, the caffeine is soluble in CO2, so it comes out of the beans, and then they can extract that. They bring it over to another container that's clean, pop the CO2 out, then they have purified caffeine, I don't know if they do a recrystallization step or anything like that, but now they have caffeine that they can sell to Monster and Red Bull and whatever the other ones are. And then they have decaffeinated coffee that they can sell to old guys like me who want to sleep at night. And so you have this fantastic solvent, CO2, which you really wouldn't think of CO2 much as a solvent, but it is. It's a good one. Ammonia would be a good solvent, but again, the pressure's higher, the temperature's higher, so it's a little more difficult to work with. We did some liquid ammonia experiments in my research as an undergraduate. I never did them because I was afraid of them. But the grad students did, and they would use liquid ammonia, and it was it wasn't supercritical ammonia. But liquid ammonia at room temperature is about 10 atmospheres, and they wanted to do this in glassware for whatever reason. Yeah. So they had some high pressure glassware setups, but that always terrified me. I never wanted to do any of the liquid ammonia experiments. Yeah, so they were doing electrochemistry, cyclic voltammetry, and liquid ammonia. So, yeah, this was not my favorite. But then look at the other end of this situation, hydrogen and helium. You know, it's pretty easy to get supercritical helium. Look at the temperature, 5 Kelvin, 2 atmospheres. Let's look over here. There's some other numbers on this table. This Boyle temperature. So that may be new for you. It's not boiling. It's not boil like B-O-I-L. It's B-O-Y-L-E. And that's the temperature at which the gas behaves ideally for a large range of pressures. So let's look at the last thing. We've got 3 minutes. And that is this compression factor. Now, this is an interesting rearrangement of the ideal gas law. PV equals nRT. So if we divide PV by nRT, we ought to get 1 for an ideal gas, because PV equals nRT. But if we don't get 1, it's not ideal. Right? And so the denominator is pretty easy to control. nRT, you know how many number of moles you have. You pick a temperature, put it in a temperature bath. And volume's pretty easy to control. And so we will pick a volume and measure the pressure. So pressure is the one we measure. It's the easiest to measure. You put it in a container, fix the temperature, you know how many moles you have, and so the pressure will tell you if it's ideal or not. Okay. And if you measure that pressure and calculate Z, these are the plots that you would get. So at a particular pressure, you measure Z and you realize, wow, I'm measuring this pressure, but it's a lot less than I expect. And I get this point right here. At 200 atmospheres, I get this point. So I've put, let's say, a mole of methane in a container at a temperature. That container has a volume, and I measure the pressure, and I get much less pressure than I expect. And so I calculate Z, and I get this value. But if I put, more gas in there, or raise the temperature. Actually, we'll pick this for a particular temperature. So I put more gas in there. Eventually, I have so much gas in there that for at 600 atmospheres, I calculate Z and I get that value. So my pressure is higher than I expect. That's weird. So an ideal gas, or a gas can be different from ideal, either too repulsive or too attractive. And so if my pressure is lower than I expect, that means my gases are attracted to each other. And if my pressure is higher than I expect, my gases are hating each other. They're pushing them into the walls with more energy. Okay, and this has this total function of how crowded the room is. I think of a dance floor. Dance floor doesn't have a lot of people on there. There's really a draw. You're like, somebody needs to dance, right? Let's go out there. And it kind of draws you on into it. So the pressure in the outside of the room is lower, right? The dance floor is pulling people. But if it's too crowded, people are like, no, I don't want to go. I'd love to dance, but I just can't. I get out there and it just pushes me back out. And so too much gas is repulsive, and too little gas is attractive. Okay, and those are 2 ways it can deviate from non-ideality. If you're at the Boyle temperature, this initial slope is 0, so it goes along for a while and then deviates. Now, if we scale all of these temperature, pressure, and volume by the critical constants, this is what we get. This is amazing. So we're taking the temperature and dividing by the critical temperature. And I know we're out of time. We got 1 minute. Volume by critical volume, pressure by critical pressure. We get what's called unitless temperature, pressure, and volume. And engineers do this all the time. Unitless variables. So anytime you hear about unitless temperature, I mean, when I first heard that, I thought, what are you talking about? Unitless temperature. It's an engineering trick. You find some value of the substance, and in this case, it's the critical temperature, pressure, and volume. And you scale the temperature, pressure, and volume by those quantities, and look what happens. This is amazing. This thing on the left, look at those dots. Nitrogen, methane, propane, ethene. It's got a double bond in there, totally different than methane. Nitrogen has a triple bond. Propane's not linear, and yet they fall on the same line. Isn't that cool? So the Z, the compression factor, is a fundamental property of gases if you scale those gases by their intermolecular attractions. So you're scaling those pressures, temperatures, and volumes by their critical constants, and then you can say, wow, gases all behave the same way.
Physical phenomenon.
Yeah, it's a true physical phenomenon, how gases bang into each other. And if you can find a way to normalize the bonding interactions or the associations, their attractions and repulsions, then you can get all the gases to behave the same way and be on the same chart. And that's why engineers do this. This is a great insight for us, that if we can normalize those attractions by dividing by their critical constants, then the gases can be understood to behave the same way. So that's a quite useful result. So we'll stop there. We'll just continue on. I'll post these notes so that you guys can prepare for the class.
Remember Dr. Hobson's PhD advisor is here, so we're meeting with him at 10 a.m. conference room in like 5 minutes.
Yes.